So what is the source of that magnetic field? We know that the source of an electric field is a stationary charge. Well, that's the source of an electric field that's constant in time. The electric field is static. Now, if those charges move, but they move with a constant velocity, they will produce a magnetic field that is constant in time. That is, they produce a static magnetic field. Now, a charge moving with a constant velocity is also known as a steady current. A current is the charge per unit time that passes a given point. A current is also a vector. Why? Because velocity is a vector. And so our current is a vector. The constant of proportionality is lambda, which is the linear charge density in coulombs per meter. In this case, our current will give us, at the point A is moving in this direction, and it will give us a magnetic field that looks somehow as though it's circulating around the current. Do you remember the right-hand rule? We point our right thumb in the direction of the current, and the fingers curl the direction of the magnetic field that is being produced. Now, the Biot-Savart Law gives us the magnetic field in Teslas at a point some distance from the source of the magnetic field. Here's the expression. The magnetic field is equal to some constants, vacuum permeability divided by 4 pi. Now we're going to integrate over the current. So dl is going to be the small element of in this case, the wire that's carrying the current. So if we integrate along dl, it means we integrate along the whole wire. We have the current at a given point crossed by the position vector, which I'll show you shortly, divided by the magnitude, that is the distance of that position vector squared. So if I draw that diagrammatically here, imagine we have a straight wire. It will give us the magnetic field at a certain point. Let's say here. And the magnetic field there, just at that point, is given by, well, we're going to start at one end and move all the way to the other end of this wire. Each time we take a small length of that wire, dl, we find the current at that point, and we take the cross product with the position vector, which starts from our element and goes to the position of interest. And we move along the wire. Here's another dl here, we take the current, and then we take the cross product with the position vector, which is now quite different. You'll notice that this 1 over r squared factor here is quite reminiscent of Coulomb's law. In fact, the Biot-Savart law has an analogous role to Coulomb's law in electrostatics. Now, once again, because we only calculate the magnetic field at this single point, if we want to map the magnetic field over a whole area or even a volume, you can see that means a lot of integrals.